Alrighty, let's take off. Picture a stack of paper. Green and white, fan-folded, the kind a computer spat out before anyone trusted a screen. A man is flipping through it days after the fact, coffee going cold, and then his pen stops. He circles 6 characters. He writes one word in the margin. Wow. He just missed it. Whatever sent that signal had already gone quiet by the time human eyes found the proof, and in almost 50 years of listening, nobody has ever heard it again. That's the thing about deep space. It doesn't call twice. It whispers once into a machine in the middle of the night and leaves us holding a piece of paper that doesn't make sense. So tonight, you're going through the file. 10 real signals. Every one of them logged, archived, time-stamped. Not stories, not hoaxes. Actual detections that actual scientists wrote down and then, in a lot of cases, very quietly stopped talking about. Some of them turned out to be us. A few of them are still just sitting there in the dark, unsolved, waiting for someone brave enough to look again. Let's start with the one that started everything. Number 1. The WOW signal. It's August 15th, 1977. A radio telescope in Ohio called Big Ear is doing what it always does, sweeping the sky, writing numbers onto paper, looking for nothing in particular. The sky drifts past it. The machine listens, and for 72 seconds, something screams. Not at random, not across the whole dial. It comes in narrow, tight, focused on a single frequency near 1420 megahertz. And that number matters, because 1420 is the note that hydrogen sings, the most common stuff in the universe, the one frequency a thinking creature anywhere might guess we'd be listening on. It's the cosmic equivalent of meeting someone under the one clock everybody knows. Nobody's watching when it happens. The telescope just records it. A few days later, an astronomer named Jerry Eman is going through the printout, line by line, and he hits a string of characters that doesn't belong. 6. E, Q, U, J, 5. To you, that looks like a password. To him, it's a measurement of how loud something got, and it got loud, far louder than the quiet hiss of empty space around it. He grabs a red pen, circles it, and writes one word next to it. You know the word. It's the name of the signal now. And then comes the part that gets under your skin. They look again. Eamon looks again. Other telescopes look again, for years, for decades, pointed right at that patch of Sagittarius where it came from. And there's nothing. Just silence, where the loudest unexplained signal in history used to be. People have tried to make it ordinary. Maybe it was a comet, breathing out hydrogen as it passed. Maybe it was a cold cloud of gas that got lit up for a moment by a flare somewhere behind it. Every explanation gets picked apart almost as fast as it's offered, because none of them quite fit something that loud, that narrow, that perfectly placed, that never came back. Here's the rule for tonight, and the WOW signal sets it. These aren't ghost stories. This is a real frequency, on a real night, written down by a real man who couldn't believe what he was reading. We just can't tell you what made it. And it's not even the strangest thing hiding in an old hard drive. Number 2, the Lorimer Burst. 2007. A scientist named Duncan Lorimer hands a student a boring job. Go through this archive of old telescope data from Australia, 6 years stale, and see if there's anything in it. Nobody expects anything. That's the whole point of grunt work. The student finds a flash, one flash, 5 milliseconds long, faster than you can blink, faster than you can decide to blink. And in those 5,000ths of a second, this thing pours out more energy than the sun manages in days. A single spike, screaming up out of the noise, and then gone before the telescope even finished the same breath. The giveaway is in how it arrives. The signal is smeared. The high notes reach the dish a hair before the low notes, like a chord played slightly out of sync. That smearing only happens when a signal plows through a huge amount of thin gas on its way to you. And the smear on this one is about 8 times more than our entire galaxy could possibly explain. Sit with that. The flash didn't come from our neighborhood. It came from outside the Milky Way entirely, from some galaxy so far off that the signal crossed an ocean of empty space just to die in an Australian dish in 2001, wait 6 years in a forgotten file, and finally get noticed. And for a while, it stands completely alone. One burst. No siblings. Plenty of serious people assume it's a glitch, a hiccup in the machine, because how can something be that bright, that brief, and that far away, and only happen once? It takes years and a lot more listening before others start turning up, and the whole world has to admit a new kind of signal exists, which means the sky had been flashing at us the entire time. We just weren't reading our own mail, but at least that one only flashed once. The next one had a pulse. Number 3, the heartbeat burst. December 21st, 2019. A telescope in Canada catches one of these fast radio bursts, and at first it looks like all the others. Quick, bright, over. Except this one doesn't end. Most of these flashes last a few thousandths of a second. This one goes on for 3 full seconds. That doesn't sound like much until you realize it's about 1,000 times longer than it has any right to be. 3 seconds of a galaxy-bright signal is an eternity. It's the difference between a camera flash and someone standing in your doorway with a floodlight. And then you look closer, and the floodlight is blinking. Inside those 3 seconds, the signal pulses. On, off, with a beat every 0.2 of a second. Steady, regular, even. Like something with a clock. Like something with a heart. The scientists who found it literally called it that, a heartbeat, because that's exactly what it looks like on the screen. A cardiac rhythm coming from a galaxy so far away, the light left it billions of years ago. Now, the honest answer is that nature can keep time. Out there spinning in the dark are neutron stars, the crushed leftovers of dead suns, cities of matter packed into something the size of a town, turning hundreds of times a second. A magnetar, a neutron star with a magnetic field strong enough to scramble you from halfway across a solar system, could in theory beat like that. In theory. Because here's what bothers people. We've caught thousands of these bursts now, and only this one had the rhythm. Just the one. A single heartbeat from a single point in the universe. And then it flatlined and never beat again. So either a dead star happened to tap out a perfect rhythm exactly once where we happened to be listening, or it wasn't quite the kind of dead we think. Either way, the next signal didn't come from billions of light years off. It came from the closest star we've got. Number 4, BLC1. There's a star called Proxima Centauri. It's the nearest one to us, a small red ember, just over 4 light years away, and it has planets, which makes it the first place anyone with a radio dish and a dream points the thing and says, please, just this once. And in 2019, a project built to hunt for alien signals points the Parkes telescope in Australia right at it. Later, going through the data, they find something, a narrow signal at 982 megahertz. Narrow the way the WOW signal was narrow, concentrated, clean, the kind of tight little spike that nature has a hard time making, and a machine makes easily. It shows up in 5 separate chunks of observation across about 30 hours. It doesn't match any satellite they know. It doesn't match any obvious source on Earth. For one electric moment, it is exactly what it looks like. A transmission from the nearest star, with planets. Word leaks, and the whole internet holds its breath, because this is the one. This is finally the one. And then they do the careful, unglamorous work. They line the signal up against everything else in the data. And buried in the noise, they find dozens of others, 36 of them, signals at other frequencies that look almost exactly like the candidate, with the same drifting shape, the same fingerprint. Signals that had already been thrown out as junk, as interference, as us. Because that's what it was. Not a message from Proxima Centauri. A faint, drifting echo of our own electronics. Some piece of equipment humming away, beating in time with the telescope's own schedule. The signal from the nearest star was a machine. The machine was just on the wrong end of the dish. And this is the part of the night that should change how you hear all of it. Every signal we've actually managed to explain, almost every single one, turned out to be this. Ourselves. Our phones, our ovens, our satellites, our broken circuits reflected back at us and dressed up like a stranger knocking. The mystery isn't usually out there. The mystery is usually a mirror, which is exactly why the ones we can't blame on ourselves are the ones that keep people up at night. Number 5, SHGB02 plus 14A. Yes, that's its name. No, it doesn't have a better one. That alone should tell you that nobody wanted to get attached. This one comes out of a project a lot of people ran without realizing it. The screensaver days, when millions of home computers chewed through telescope data while their owners slept. And out of all that crunching, one candidate floats to the top. Detected 3 times. About a minute of signal in total. Sitting right around 1420 megahertz again, the hydrogen note, the channel everyone watches. And then it starts doing things that don't add up. The signal drifts. Its frequency slides, fast. And if you try to explain that drift the normal way, as the wobble of something spinning, you get a planet turning on its axis about 40 times faster than Earth. A day that lasts less than an hour. Fine, strange, but okay, except every time the signal reappears, it snaps back to where it started, to that same 1420, as if something keeps resetting it. A drift that fast shouldn't politely return to the same starting line. This one does. And then you check where it's coming from, and the floor drops out. You trace the direction back, out past Pisces, toward Aries, and there's nothing there. No star within 1,000 light years. An empty stretch of sky. The signal is coming from a place where, as far as we can see, there is nothing to send it. So take your pick. It's a planet that spins impossibly fast around a star we can't find. Or it's a flicker of noise that happened to look like all of that. The people who found it never claimed it was aliens. They also never managed to make it make sense. And then it slipped off the front page and stayed there. The next one didn't make a sound at all. It just turned out the lights. Number 6, Tabby's star. Here's where we change the rules. Because this signal isn't a sound. It's a shadow. There's a star, an ordinary looking one, with a catalog number and a nickname after the scientist who put it on the map. And a telescope built to watch stars dim ever so slightly as planets cross in front of them is staring at thousands of stars at once. When a planet the size of Jupiter passes across a star, the star dims by about 1%. A polite little dip. Barely there. This star dims by 22%. Not once on a schedule, the way a planet would. Irregularly. Unpredictably. Deep, jagged drops, like something enormous and lumpy and wrong is drifting across its face, blocking nearly a quarter of an entire sun and then getting out of the way. No planet does that. No planet is anywhere near big enough to do that. So people start saying the word out loud. Megastructure. Some vast thing built around a star to drink its energy. The kind of object a civilization far past us might assemble, casting a colossal, uneven shadow as it turns. Serious scientists float it, not as a joke, but as a thing they genuinely can't rule out. And for a while, this little star becomes the most famous question mark in the sky. The calmer answer, the one most of the field settles toward, is dust. A great cloud of fine grains orbiting the star, swallowing some colors of light more than others in a way a solid object wouldn't. Dust dims you unevenly. A wall dims you flat, and the dimming here favors dust. Probably. The honest version is that the exact pattern still isn't fully pinned down, and a star that drops a fifth of its light for reasons we're still arguing about is not a closed case. It's a shadow we can measure and can't quite name. The next signal we could name. We just weren't allowed to know about it. Number 7. HD 164595. This one's a story about people as much as space. May 2015. A Russian radio telescope, a strange ring of an instrument, is pointed toward a sun-like star in the constellation Hercules, a star not so different from our own, about 95 light-years away. And for 2 seconds, it catches a blip, a pulse of radio energy at 11 gigahertz, a high, sharp frequency that's unusual for nature to produce with that kind of power. And then, the team does something that, depending on how you look at it, is either careful science or a year-long held breath. They don't announce it. They sit on it. For over a year, this possible signal from a sun-like star just lives quietly in their files while the rest of the world has no idea, until it leaks. Mid-2016, word gets out, and the reaction is instant and enormous. Headlines. Telescopes swinging around to look. That same electric, maybe this is it feeling. The one Proxima gave us. The one the WOW signal gave us. Racing around the planet again. And then it deflates. Fast. Because the signal was heard once. For 2 seconds. By one telescope. Nobody else ever caught it. And a single unrepeated blip from a single dish, at a frequency that happens to be great at picking up our own interference, is not a phone call from Hercules. The official verdict comes down quietly, most likely from right here on Earth. On the scale scientists use to rank these candidates, it barely registers. So it joins the pile. Another maybe that turned out to be a mirror, or close enough to one. But notice what it really shows you. Not the signal. The silence around it. A real detection can sit in a drawer for a year while the people who found it decide whether to even say it out loud. Makes you wonder what's in the other drawers, especially the one with the thing near the center of the galaxy. Number 8. ASKAPJ 1736. Near the heart of the Milky Way, where the stars crowd together and a giant black hole sits at the center of it all, a telescope in Australia finds a point of light that will not behave. They nickname it after the young scientist who spotted it, because its real name is a phone number, and from the start it does everything wrong. It appears. Then it brightens. Hard. By a factor of 100, like a dim spark suddenly flaring to the strength of a floodlight. Then it fades. Then it vanishes completely, sometimes for weeks. Then it comes back. There's no schedule, no clean rhythm you can set a clock to. It switches on and off across timescales, from a single day to many weeks on its own terms, like something deciding when it wants to be seen. And its light is doing something even stranger. The radio waves are extremely polarized, all oscillating in one direction. And that direction rotates over time, twisting as you watch. That's not how most things in the sky behave. So the obvious suspects line up, and one by one they get crossed off. A flaring star? No. There's nothing there at any other wavelength. No star. No glow invisible light or infrared or X-rays. Nothing but the radio. A supernova? A known kind of dead star? A binary? A gamma-ray burst? The behavior fits none of them. It is a thing that is bright in radio and completely invisible in everything else, flickering near the most crowded, most violent corner of our galaxy. The leading guess isn't really an answer. It's an admission that this might be a whole new class of object we've only just started to notice and don't yet understand at all. And if a thing that flickers on its own schedule unsettles you, wait until you meet the one that runs on a clock. Number 9. GLEAM-X. found, like so many of these, by going back through old data. In this case, from a low-frequency array out in the Australian desert. And what someone finds in those 3 months of early 2018 breaks a rule physicists thought was solid. Something turned on every 18 minutes. Not roughly. Not on average. Every 18 minutes and change, for 30 to 60 seconds at a time, this source blasts out a burst of coherent, highly organized radio energy, one of the brightest things in that whole patch of sky, beating like a lighthouse with a beam too regular to be an accident. Then it switches off. 18 minutes later, it does it again. For 3 months. And then, that March, it goes silent and hasn't been heard from since. Here's why that 18 minutes is a problem. The objects that pulse like this, neutron stars again, those crushed dead suns, only manage it because they spin fast, whipping a beam past us many times a second. As they slow down over millions of years, they cross what astronomers actually call a death line, a point past which they should go dark. Too slow to emit. A neutron star turning once every 18 minutes is so far past that line it shouldn't be making radio at all. And yet, there it was. For 3 months, something on the wrong side of the death line ran a near-perfect clock, 18 minutes a tick, and then quit. The best explanation is an exotic kind of magnetar, a dead star with a magnetic field so monstrous it can break the normal rules and keep shining long after it should have gone quiet. The best explanation, in other words, is that we have to bend the physics to fit the signal, which is not the same as understanding it. But every signal so far has had a where, a direction, a point in the sky. The last one is everywhere at once. Number 10, the cosmic hum. Forget radio for a second. Forget light entirely. The last signal isn't something you could ever point a dish at because it isn't traveling through space. It is space, moving. In June of 2023, after 15 years of work, teams of scientists around the world announced the same impossible-sounding thing. The fabric of the universe is humming. There is a low, slow ripple running through everything. Gravitational waves, actual stretches and squeezes of distance itself, washing across the entire galaxy at once. You can't hear it. You can't feel it. The waves are so enormous that a single one can take years, even decades, to roll past. And as it does, it changes the distance across the whole Earth by less than the width of an atom. It's happening to you right now. You are being gently stretched and compressed by a tide soaked into reality, and you will never notice. So how do you catch something like that? You use the dead stars again. Scattered across the galaxy are pulsars, neutron stars that flash with such insane regularity. They're basically the most accurate clocks in existence. The scientists watched dozens of them, 67, ticking away across the sky, for 15 years, looking for the waves to nudge those ticks ever so slightly early and late in a very particular, coordinated pattern. And the pattern showed up. The exact shape that the laws of gravity predicted a sea of these waves would leave behind. What's making it? The leading answer is almost too big to hold. Pairs of supermassive black holes, the monsters at the centers of galaxies, spiraling toward each other across the whole history of the cosmos, each merger sending out ripples that pile up into one endless background hum. The sound, if it were a sound, of every galaxy that ever collided, blended together into a single low note that never ends. And it's passing through you as you sit here. So that's the file. 10 signals out of the dark. A few of them, like Proxima and Hercules, turned out to be us all along. Our machines, our noise, a mirror dressed up as a stranger. Some, like the wow signal, are still just sitting there, logged, real, and unexplained after half a century. And the last one isn't a message at all. It's the universe itself humming. The sky is full of signals. Most are noise. A handful are waiting, and you'll probably never know which was which.